Hello there, and welcome to the Sleepy Science Society. I'm so glad you found your way here tonight. Maybe you've had a long day filled with visible things, tangible things, things you could touch and see and measure. Or maybe you're the kind of person who finds peace in pondering the great mysteries, the questions that stretch beyond what our eyes can perceive. Either way, tonight's journey is for you. You have nothing to do but rest. Let your breathing slow, your muscles relax, and your mind drift gently into the depths of one of science's most profound puzzles. Tonight, we're exploring something extraordinary, something that makes up most of the matter in the universe, something that holds galaxies together, something that shaped the very structure of the cosmos as we know it. And yet, despite its overwhelming presence, despite its fundamental importance to everything that exists, we cannot see it. We cannot touch it. We can barely detect it at all. We're talking about dark matter, the invisible scaffolding of the universe, the hidden architecture that keeps everything from flying apart into the endless void. Before we begin our gentle drift through this cosmic mystery, if these calm explorations help you unwind at the end of your day, or if they give you a quiet way to learn while you rest, consider liking this video and subscribing to the channel. It helps others find their way here too, one sleepy, curious soul at a time. Now, let your eyes grow heavy. Let the world fade softly into the background, and let's begin our journey into the invisible universe. Imagine for a moment that everything you've ever seen, every star in the night sky, every planet, every grain of sand on every beach, every tree, every building, every person, every atom in your own body, all of it together makes up less than 5% of what actually exists. The rest, the overwhelming majority of the universe, is made of things we cannot see. Things that don't shine, don't reflect light, don't interact with the electromagnetic force that allows us to perceive almost everything around us. This invisible majority comes in two forms. There's this dark energy, which we'll save for another night, making up about 70% of everything. And then there's dark matter, accounting for about 25% of the universe's total mass and energy. Together, these dark components make up 95% of the cosmos. We live in a universe where the familiar is the exception, where the visible is the minority, where what we can touch and see is barely a whisper of what truly exists. Dark matter isn't just some abstract concept dreamed up by theoretical physicists with too much time on their hands. It's real. It's here. Right now, as you rest wherever you are, dark matter particles are passing through your body. Trillions upon trillions of them, streaming through you, through the walls around you, through the earth itself, barely interacting with anything at all. They're ghosts of a sort, but ghosts that shape reality itself. Without dark matter, galaxies wouldn't exist as we know them. Stars wouldn't have formed the way they did. The universe would be a fundamentally different place, and we, in all likelihood, wouldn't be here at all. The story of dark matter is a story about seeing the invisible, about detecting presence through absence, about following clues that lead to one of the most profound realizations in the history of science. It's a story that spans nearly a century, from early hints and dismissals to overwhelming evidence that forced the scientific community to accept that most of the universe had been hidden from view all along. It's a story that continues today, as physicists around the world search in underground laboratories, in space-based telescopes, and in the most powerful particle accelerators ever built, all trying to catch a glimpse of these elusive particles that seem to be everywhere and nowhere at once. Tonight, we'll trace that story together. We'll discover how astronomers first realized something was wrong, how the evidence accumulated until it could no longer be ignored, what we know about dark matter's properties, and what mysterious particles might make up this invisible cosmic component. We'll explore the experiments designed to catch dark matter in the act, the competing theories about its nature, and the implications for our understanding of the universe itself. So settle in, let your breathing deepen, and prepare to explore a universe far stranger and more mysterious than anyone imagined just a few generations ago. The discovery, when the universe stopped making sense. Our story begins in 1933, in a time when the universe seemed to be opening up before human understanding like a flower in bloom. Edwin Hubble had recently discovered that the universe was expanding, pushing the boundaries of space itself outward in all directions. Astronomers were mapping the cosmos with increasingly powerful telescopes, revealing galaxies beyond our own, island universes separated by vast gulfs of emptiness. It was an exciting time to study the heavens, a time when each new observation seemed to bring clarity to the grand cosmic picture. And then a Swiss-American astronomer named Fritz Zwicky looked at something that didn't make any sense at all. Working at the California Institute of Technology, using the mighty Mount Wilson Observatory that perched above the Los Angeles basin, Zwicky turned his attention to the Coma Cluster. This wasn't just any collection of galaxies. The Coma Cluster is enormous, containing over 1,000 galaxies all bound together by their mutual gravitational attraction, dancing in a cosmic waltz that had been going on for billions of years. These galaxies weren't just sitting still. They were moving, orbiting around their common center of mass, pulled by gravity into complex patterns of motion. Zwicky could measure how fast these galaxies were moving by observing the Doppler effect, the same phenomenon that makes an ambulance siren change pitch as it passes you on the street. When a galaxy moves toward us, its light shifts slightly toward the blue end of the spectrum. When it moves away, the light shifts toward red. By carefully measuring these shifts, Zwicky could calculate the velocities of individual galaxies within the cluster. And what he found troubled him deeply. The galaxies were moving far too fast. When he calculated how much mass the cluster needed to hold these speeding galaxies in place, to keep them from flying off into intergalactic space, he found something shocking. The visible mass of all the stars in all the galaxies wasn't nearly enough, not even close. In fact, when he did the mathematics, Zwicky discovered that the visible matter in the Coma Cluster could account for only about 1% of the mass needed to keep the cluster gravitationally bound. 1%. That meant 99% of the cluster's mass was missing. Or rather, it was there. It had to be there to explain the motion he was observing, but it wasn't emitting any light. It wasn't visible in any telescope. It was dark. Zwicky, working in German, called this mysterious substance Dunkle Materie, dark matter. The name stuck, though the reality it described was so strange that many of Zweiky's colleagues were skeptical. Maybe his measurements were wrong. Maybe there was some other explanation. Maybe the galaxies weren't really bound at all, but were just passing through and would eventually disperse. The problem, many thought, would go away with better observations. But Zwicky wasn't the first to suspect that the universe might contain more than meets the eye. Decades earlier, in the late 19th century, the brilliant physicist Lord Kelvin had contemplated the stars near our own sun. Using observations of how these stars moved through space, their velocities and distributions, Kelvin tried to estimate how many stars must exist in our cosmic neighborhood, including those too faint or too distant to see directly. His calculations suggested that many stars must be dark bodies, stars we couldn't detect, but whose gravity influenced what we could see. He was speculating about ordinary stars that just happened to be dim or distant, not about fundamentally different matter, but he had touched on an idea that would echo through astronomy. Not everything that exists announces its presence with light. In the early 20th century, Dutch astronomer Jacobus Kapteyn, one of 15 children raised in a boarding school run by his parents, found himself appointed to a professorship in astronomy without the funds to buy a proper telescope. Undeterred, he partnered with astronomers in South Africa who could photograph the southern sky, and he spent years meticulously measuring the positions of hundreds of thousands of stars by hand. His work helped map the structure of the Milky Way, and in a paper published in 1922, just weeks before his death, Kapteyn mentioned dark matter as he discussed the material between the stars. Again, he was thinking primarily of ordinary matter that was hard to see, but the phrase entered the scientific lexicon, waiting for its true meaning to be discovered. Then came Zwicky's bombshell. But even with such a dramatic finding, the scientific community moved slowly. The missing mass in the Coma cluster was puzzling, certainly, but was it real? In 1939, American astronomer Horace Babcock observed something similar in the Andromeda Galaxy. When he measured the rotation of this great spiral, he found that the outer regions were spinning faster than expected based on the visible mass. Rather than concluding that invisible matter must exist, Babcock suggested other possibilities. Perhaps light was being absorbed within the galaxy, or perhaps the laws of dynamics worked differently in the outer regions of spirals. The idea that most of the universe might be invisible was still too radical to embrace fully. A year later, Jan Oort, studying our own galaxy, found evidence of substantial non-visible mass in a large halo surrounding the visible disk of the Milky Way. The pattern was emerging, but slowly, like a picture developing in a darkroom, still too faint to see clearly. For decades, these observations lingered on the edges of astronomy. They were curiosities, anomalies, problems to be solved eventually, perhaps, but not the revolutionary discoveries they would later prove to be. The universe, it seemed, was trying to tell us something, but we weren't quite ready to listen. Not yet. That would take another generation, another set of observations, and one astronomer's patient, meticulous work that would finally force the scientific world to confront the invisible. Vera Rubin and the rotation that changed everything. The woman who would ultimately prove the existence of dark matter beyond reasonable doubt didn't start out expecting to revolutionize cosmology. Vera Rubin was an American astronomer who faced considerable obstacles in her career simply because she was a woman in a field dominated by men. When she applied to graduate school at Princeton in the late 1940s, she was rejected because the astronomy program didn't accept women. They wouldn't admit female students until 1975, decades after Rubin had already made groundbreaking discoveries elsewhere. But such barriers, while frustrating and unjust, didn't stop her. She earned her doctorate, raised 4 children, and pursued the questions that fascinated her with quiet determination. In the 1970s, working at the Carnegie Institution for Science with her colleague Kent Ford, Rubin turned her attention to the rotation of spiral galaxies. These magnificent pinwheels of stars, hundreds of billions of suns arranged in graceful curved arms, rotate around their centers like cosmic carousels. But how do they rotate? Do stars farther from the center move more slowly than those closer in, like planets in our solar system where distant Neptune crawls along at a fraction of Mercury's orbital speed? Or does something else govern their motion? To find out, Rubin and Ford measured the velocities of stars at various distances from the centers of spiral galaxies, using the same Doppler technique that Zwicky had employed decades earlier. They expected to see what basic physics predicted. Stars near the bright, densely packed galactic center should orbit quickly, held in tight, fast orbits by the strong gravitational pull of all that concentrated mass. Stars farther out, in the sparse outer regions where starlight fades to a whisper, should orbit much more slowly, barely held by the weak gravitational influence of the distant core. Planets in our solar system follow exactly this pattern. Mercury whips around the Sun in just 88 days, while distant Neptune takes more than 160 years to complete one orbit. The relationship is precise and predictable. The farther you go from a central mass, the slower your orbital speed should be. This is a fundamental consequence of gravity, as described by Isaac Newton more than 3 centuries ago. But that's not what Rubin and Ford saw, not at all. Instead, they discovered something completely unexpected. Stars far from the galactic centers were moving just as fast as stars much closer in. The rotation curves, graphs showing orbital velocity versus distance from the center, didn't drop off as they should. Instead, they flattened out, remaining roughly constant even in the distant outer reaches where hardly any visible stars existed. It was as if the galaxy's gravitational pull wasn't weakening with distance the way it should. As if something unseen was adding its gravity to the mix, pulling on those distant stars, keeping them moving faster than they had any right to move. At first, it was just one galaxy showing this peculiar behavior. Perhaps this spiral was unusual in some way, an outlier that didn't represent the general pattern. So Rubin and Ford observed another galaxy. Same result. And another. Same thing. They expanded their survey, looking at 60 different spiral galaxies, choosing them carefully to represent different sizes, different brightnesses, different orientations. Every single one showed the same flat rotation curve. Every single one required far more mass than could be accounted for by its visible stars. The conclusion was unavoidable. What you see in a spiral galaxy, Rubin said, is not what you get. Her calculations showed that galaxies must contain roughly 10 times as much dark mass as luminous mass. 10 times. 90% of a galaxy's matter was invisible, detectable only through its gravitational effects on the stars we could see. This wasn't an anomaly in one distant cluster, as Zwicky had found. This was a fundamental property of galaxies themselves, including our own, Milky Way. We live in a galaxy where 90% of the matter cannot be seen, streaming invisibly through the space between stars, forming a vast halo that extends far beyond the visible disk, holding everything together with its patient, invisible grip. Rubin's work was careful, thorough, and impossible to dismiss. She had followed the scientific method meticulously, observing dozens of galaxies, checking and rechecking her measurements, considering alternative explanations. And when she looked back through the literature, she remembered something from her graduate school days. Fritz Zwicky's old paper about the Coma cluster. Zwicky had been right. The missing mass was real. Dark matter existed, not just in one cluster, not just in one galaxy, but everywhere. It was a fundamental component of the universe, more abundant than the ordinary matter that makes up stars and planets and ourselves. The cosmos we thought we knew was just the tip of the iceberg, the visible surface of a much deeper reality. The astronomy community, presented with such overwhelming evidence, couldn't ignore it anymore. Through the 1970s and 1980s, other researchers confirmed Rubin's findings. Sandra Faber, studying elliptical galaxies, found they too were embedded in dark matter halos. In 1979, Faber and John Gallagher published a comprehensive review article that convinced the scientific community that dark matter wasn't speculation or error, but a real, major constituent of the universe. By 1984, researchers were writing papers about how the universe had evolved under the influence of cold dark matter, treating it as a known factor in cosmic evolution. The paradigm had shifted. We had discovered, through patient observation and careful reasoning, that most of the universe had been invisible all along. Rubin herself never sought fame for these discoveries. She was content with the personal satisfaction of understanding, of peering into the cosmic darkness and seeing something no one had seen before. "We have peered into a new world," she wrote, "and have seen that it is more mysterious and more complex than we had imagined. Still, more mysteries of the universe remain hidden. Their discovery awaits the adventurous scientists of the future. I like it this way." For her groundbreaking work, Rubin was elected to the National Academy of Sciences and awarded the National Medal of Science. But perhaps more importantly, she had opened a door to a new understanding of the cosmos, one where the invisible is more abundant than the visible, and where mystery lies at the heart of existence itself. What dark matter actually is and isn't. So, what exactly is this dark matter that makes up most of the universe's mass? The honest answer is, we don't fully know. But we've learned quite a bit about what it does and doesn't do, about its properties and behavior, even if we can't yet point to it and say, "This is it. This is the Oz particle. This is what dark matter is made of." Think of it like this. Imagine trying to understand wind without ever being able to see it or feel it directly. You could watch leaves move, see waves on water, observe clouds drift across the sky, and from all these effects you could deduce that something invisible is pushing things around. Something with direction and force and predictable patterns. You'd know a lot about wind even without seeing it directly. That's where we are with dark matter. We see its effects everywhere, and from those effects we can deduce quite a bit about what it must be like. First and foremost, dark matter does not interact with light. At all. It doesn't emit light the way stars do, burning through nuclear fusion and radiating energy across the electromagnetic spectrum. It doesn't absorb light the way dust clouds do, blocking the starlight that passes through them. And it doesn't reflect light the way planets and moons do, shining with borrowed brilliance from their parent stars. Dark matter is completely transparent to electromagnetic radiation. Light passes through it as if it weren't there. This is why we call it dark. Not because it's some shade of black, but because it doesn't participate in the electromagnetic interactions that allow us to see, well, anything. This means we can't photograph dark matter. We can't detect it with optical telescopes or radio telescopes or infrared cameras or X-ray detectors or any of the instruments that have revealed so much of the cosmos to us. All of these instruments work by catching photons, particles of light that interact with matter through the electromagnetic force. But dark matter doesn't play that game. It sits outside the electromagnetic force entirely, invisible to any form of light, no matter the wavelength. What dark matter does interact with is gravity. This is the key, the one handle we have on this elusive substance. Dark matter has mass, and mass creates gravity, and gravity affects everything around it. When a cloud of dark matter sits in space, its gravitational pull bends space-time itself, curving the fabric of the cosmos the way a bowling ball creates a depression in a stretched rubber sheet. Anything passing through or near this warped space-time feels its influence. Stars orbit faster in the outer regions of galaxies because dark matter's gravity pulls on them. Galaxy clusters hold together despite the furious speeds of their member galaxies because dark matter provides the gravitational glue. The universe developed structure, condensing from a smooth primordial state into the filaments and clusters and voids we see today, because dark matter's gravity provided the scaffolding around which ordinary matter could collapse and form galaxies. We can also say with confidence that dark matter is cold, at least in cosmic terms. This doesn't mean it has a temperature measured in degrees Celsius or Fahrenheit. Rather, cold in this context means that dark matter particles move relatively slowly compared to the speed of light. They're non-relativistic, drifting through space at speeds that, while perhaps very fast by everyday standards, are sedate compared to particles like neutrinos that zip around at nearly light speed. This matters because cold dark matter can clump together, can condense into halos around galaxies, can create the structures we observe. Hot dark matter moving at relativistic speeds would be too energetic to settle down into the relatively small-scale structures like galaxies. The evidence strongly suggests that dark matter is cold, patient, gathering slowly under its own gravity over billions of years. Dark matter also appears to interact very weakly, if at all, with ordinary matter through any force other than gravity. It's not just that it doesn't interact electromagnetically, it also doesn't seem to interact through the strong nuclear force that binds atomic nuclei together, or, significantly, through the weak nuclear force that governs certain types of radioactive decay. dark matter particles can pass through ordinary matter almost as if it weren't there. They can pass through the entire Earth without bumping into anything, without scattering, without leaving any trace except the slight gravitational tug they exert as they pass. This extreme non-interaction is both a blessing and a curse for scientists. It's a curse because it makes dark matter extraordinarily difficult to detect. You can't catch something that passes through your detector as if it were perfectly transparent. But it's also a blessing in a strange way because it means that dark matter doesn't lose energy easily. Ordinary matter can radiate energy away as light or heat, can collide with other particles and convert kinetic energy into other forms. This ability to lose energy is what allows ordinary matter to condense into dense objects like planets and stars. Dark matter, unable to radiate energy or interact significantly with itself, can't collapse into dense, compact objects. It spreads out into vast, diffuse halos, surrounding galaxies like invisible fog, present everywhere but never concentrated into the tight configurations we associate with ordinary matter. There's another crucial property. Dark matter appears to be stable, or at least very long-lived. If dark matter particles were constantly decaying into other particles, we'd see evidence of those decay products, flashes of radiation, or cascades of particles streaming from regions of high dark matter density. But we don't see that. Dark matter, whatever it's made of, seems to last essentially forever, persisting unchanged from the early universe to the present day. It was created, somehow, in the first moments after the Big Bang, and it's still here, making up the majority of matter in the cosmos, as patient and unchanging as anything in the universe can be. We also know roughly how much dark matter there is. Measurements of the cosmic microwave background, radiation, the faint glow left over from the Big Bang, allow scientists to determine the matter-energy content of the universe with remarkable precision. These measurements tell us that dark matter makes up about 27% of the total mass energy of the universe. Ordinary matter, the stuff that makes up stars and planets and us, accounts for only about 5%. The rest is dark energy, something even more mysterious that we won't delve into tonight. But focusing on matter alone, dark matter outweighs ordinary matter by more than 5 to 1. For every atom in your body, for every star in the sky, there are 5 times as many dark matter particles drifting invisibly through space. This ratio has profound implications. It means the universe's structure, its evolution, its very nature has been shaped primarily by something we can't see. Ordinary matter, the stuff we're made of, is almost an afterthought in cosmic terms, a minor component that happens to interact with light and thereby grabs our attention. But the real story of the universe, the deep structure that underlies everything, is written in dark matter. We're like sailors on an ocean, able to see only the surface while the vast bulk of the water extends into invisible depths beneath our keels. And yet, those invisible depths determine the ocean's currents, its movements, its entire character. So too with dark matter and the cosmos. Evidence from multiple sources. The rotation curves of galaxies and the velocities in galaxy clusters are compelling evidence for dark matter. But science demands multiple independent lines of evidence before accepting something as fundamental as an invisible substance making up most of the universe. Fortunately, dark matter leaves its fingerprints everywhere. Once astronomers knew what to look for, they found confirmation after confirmation, each observation adding another piece to the puzzle, each measurement reinforcing the reality of this cosmic phantom. Perhaps the most dramatic evidence comes from gravitational lensing. Einstein's general theory of relativity, published in 1915, revolutionized our understanding of gravity by showing that mass doesn't just pull on other mass through some mysterious action at a distance. Instead, mass warps the very fabric of space and time. Imagine space-time as a stretched rubber sheet, and massive objects as heavy balls placed on that sheet. The sheet curves around them, and anything moving nearby follows the curves, appearing to be pulled toward the massive object. But light is affected too. A beam of light traveling through curved space-time follows the curves, bending its path in a predictable way. This means that a massive object can act like a cosmic lens, bending light from more distant sources that pass near it. If a massive galaxy or galaxy cluster sits between us and a more distant galaxy, the light from that distant galaxy gets bent as it passes through the warped space-time around the intervening mass. We might see multiple images of the background galaxy, or see it stretched into arcs and curves, its appearance distorted by the gravitational lens. And here's the key. The amount of distortion depends on the total mass of the lens, not just the visible mass. Dark matter contributes to the lensing just as much as luminous matter does. Astronomers use this principle to map the distribution of dark matter directly. By carefully measuring how background galaxies are distorted, they can reconstruct the mass distribution of the lensing cluster, creating maps that show where all the mass is located, both visible and invisible. And what they find is stunning. Time and again, these gravitational lensing maps show massive concentrations of matter in places where hardly any visible matter exists. The dark matter reveals itself through its gravitational fingerprint, bending light into telltale patterns that can't be explained by the stars and gas we can see. The most dramatic example of this comes from the Bullet Cluster, a system where two galaxy clusters have collided and passed through each other. When this happened, something remarkable occurred. The galaxies themselves, being mostly empty space, passed through each other relatively unaffected, like two swarms of fireflies interpenetrating without colliding. But the hot gas that fills the space between galaxies, observable through the X-rays it emits, behaved differently. As the two clouds of gas collided, they slammed into each other, creating friction and drag that slowed them down. The gas, which makes up most of the normal matter in the clusters, ended up lagging behind. But when astronomers used gravitational lensing to map where most of the mass was located in the Bullet Cluster, they found something extraordinary. The center of a mass, the location of the gravitational lensing, didn't coincide with the hot gas visible in X-rays. Instead, it lined up with the galaxies, which had passed through unimpeded. This makes perfect sense if dark matter exists. The dark matter, interacting only through gravity and not affected by friction or collisions, would have passed through along with the galaxies, leaving the ordinary matter behind. The bullet cluster shows us dark matter and ordinary matter behaving differently during a collision, providing clear visual evidence that most of the mass is something other than the gas and stars we can see. Another powerful line of evidence comes from the cosmic microwave background, or CMB. This is the oldest light in the universe, radiation that has been traveling through space for more than 13 billion years, since just 380,000 years after the Big Bang. At that time, the universe had cooled enough for atoms to form, allowing light to travel freely for the first time. That light, stretched by cosmic expansion into microwave wavelengths, reaches us today from every direction in the sky, carrying information about the conditions in the very early universe. The CMB isn't perfectly uniform. It has tiny temperature fluctuations, variations of only about 1 part in 100,000. But these variations are crucial. They represent the seeds from which all cosmic structure would eventually grow. And the pattern of these fluctuations, their sizes and strengths, depends critically on the matter content of the universe. By analyzing the CMB in exquisite detail, as done by satellites like WMAP and Planck, scientists can determine precisely how much ordinary matter and dark matter existed in the early universe. The results match perfectly with what we see in galaxies and clusters today. The CMB tells us that dark matter makes up about 27% of the universe's mass energy, exactly what's needed to explain the motions of galaxies and the structure we observe. This consistency across completely different types of observations, from galaxy rotation curves measured with optical telescopes to subtle temperature variations in microwave radiation from the dawn of time, provides compelling confirmation that dark matter is real. Yet another piece of evidence comes from the large-scale structure of the universe itself. When astronomers map the distribution of galaxies across vast distances, they find that galaxies aren't scattered randomly. Instead, they're organized into a cosmic web, with filaments of galaxies stretching across hundreds of millions of light years, surrounding enormous voids where hardly any galaxies exist. This web-like pattern emerged from tiny density variations in the early universe, regions that were slightly more dense than their surroundings and therefore had slightly stronger gravity. In the billions of years since the Big Bang, gravity amplified these tiny differences. Denser regions pulled in more matter, becoming denser still, eventually collapsing into the galaxies and clusters we see today. But here's the thing. Computer simulations show that this process couldn't have happened fast enough with ordinary matter alone. Radiation pressure and other effects would have smoothed out the density variations before they could grow large enough to form galaxies. But add dark matter to the simulation, and everything works. Dark matter, unaffected by radiation pressure, could start clumping immediately after the Big Bang, creating gravitational wells that ordinary matter could later fall into. The cosmic web is exactly what we'd expect if dark matter dominated the universe's mass, providing the scaffolding around which galaxies formed. All of these different lines of evidence, galaxy rotation curves, galaxy cluster velocities, gravitational lensing, the cosmic microwave background, and large-scale structure formation, point to the same conclusion. Dark matter exists. It's real. It's here. It makes up most of the matter in the universe. The evidence is overwhelming, coming from completely different types of observations using completely different techniques, all converging on the same picture. Science rarely provides such unanimous confirmation, but in the case of dark matter, the universe itself seems to be shouting that this invisible substance is a fundamental part of reality. Dark matter. Throughout the cosmos, now that we understand dark matter exists, where is it? The answer is both simple and profound. It's everywhere. Right now, as you rest listening to these words, you're immersed in dark matter. The Earth is moving through a vast cloud of dark matter particles, a diffuse fog that fills our galaxy and permeates the space between galaxies. These particles are passing through your body at this very moment. Billions or trillions of them every second, entering through one side and exiting through the other without interacting with a single atom of your flesh or bone. You're transparent to them, and they to you. Ships passing silently in the night. Our solar system sits within the Milky Way's dark matter halo, an enormous, roughly spherical cloud of dark matter that surrounds the visible disk of our galaxy. This halo extends far beyond the last visible stars, reaching out perhaps 10 times farther than the luminous matter. Most of the Milky Way's mass resides in this dark halo, not in the bright spiral arms that glow so beautifully in photographs. When we look up at the Milky Way's band of starlight crossing the sky, we're seeing only a small fraction of our galaxy's true extent. The real Milky Way, measured in mass, is this vast dark envelope within which the visible galaxy sits like a bright jewel in a much larger setting. The density of dark matter in our cosmic neighborhood isn't very high by everyday standards. Estimates suggest that within each cubic centimeter of space near the solar system, there's perhaps about 1/3 of a proton's worth of dark matter. That doesn't sound like much, and in terms of density, it isn't. Empty space, by human standards, is still very empty even with dark matter in it. But when you add up all that dark matter across the vast volume of the galactic halo, it amounts to tremendous mass, far more than all the stars in the Milky Way combined. The distribution of dark matter isn't uniform. It's denser near the centers of galaxies and thins out toward the edges. Computer simulations of dark matter halos show them forming complex structures, with the bulk in a relatively smooth distribution, but also featuring smaller clumps and streams, substructure inherited from the way dark matter assembled over cosmic time. Some of these clumps might be remnants of smaller dark matter halos that merged into the Milky Way, captured as our galaxy grew by swallowing its smaller neighbors. Others might be regions where dark matter naturally concentrated due to the complex dynamics of gravitational collapse. Between galaxies, in the vast intergalactic gulfs, dark matter still exists, but more thinly spread. Yet even here, it's not absent. Dark matter forms at the cosmic web, filaments of heightened density stretching between galaxy clusters, like the strands of a spider's web spanning across emptiness. These filaments are where galaxies formed, drawn together along lines of dark matter concentration. In the largest voids, the great empty regions between filaments, dark matter density drops to its lowest, but never quite disappears. Everywhere in the observable universe, dark matter is present to some degree, the invisible majority that shapes cosmic geography. Galaxy clusters, those immense congregations of hundreds or thousands of galaxies, sit within even more massive dark matter halos. The Coma cluster, where Fritz Zwicky first found evidence of missing mass, is embedded in a dark matter halo weighing perhaps 100 trillion solar masses. That's more than the mass of all the visible galaxies in the cluster combined, multiplied many times over. When we look at a rich cluster of galaxies, the bright points of light we see are floating within a vast, invisible ocean of dark matter that provides most of the cluster's gravitational binding. Gravitational lensing studies have allowed astronomers to map dark matter distributions in exquisite detail for many clusters. These maps show dark matter concentrated around the densest regions where galaxies congregate, but also reveal the three-dimensional structure of the dark matter halos. They're not perfect spheres, but show variations and substructure, evidence of the complex history of how these massive systems assembled over billions of years through the merger of smaller structures. Each map is like an X-ray, revealing the skeleton beneath the visible skin of the cluster, showing the hidden architecture that gives the cluster its shape and holds it together. On the very largest scales, dark matter dominates the structure of the universe itself. The cosmic web, that grand network of filaments and voids spanning billions of light years, is primarily a dark matter structure. Ordinary matter, following the gravitational pull of dark matter concentrations, collected along the filaments and formed galaxies. But the underlying framework, the scaffolding that defines the web's shape, is made of dark matter. In a very real sense, we live in a dark matter universe where ordinary matter is sprinkled like seasoning, concentrated here and there into luminous pockets we call galaxy, but always following the deeper template laid down by the invisible majority. This omnipresence of dark matter has profound implications. It means that dark matter isn't some exotic phenomenon confined to distant galaxies or the early universe. It's here, now, an integral part of the cosmos at every scale. The Earth moves through it as we orbit the Sun. The Sun carries its retinue of planets through it as we orbit the galactic center. The Milky Way itself swims through the local group's collective dark matter halo. At every level, from local to cosmic, dark matter shapes the gravitational landscape, defines the structure, and provides the unseen foundation upon which everything visible rests. The leading candidates, WIMPs. So we know dark matter exists. We know it's everywhere. We know many of its properties. But what is it made of? What particles compose this invisible cosmic component? For decades, the leading candidate has been something called a WIMP, an acronym for Weakly Interacting Massive Particle. The name describes its properties. It's massive, meaning it has substantial mass compared to, say, an electron, and it interacts weakly, meaning it doesn't participate in electromagnetic or strong nuclear interactions, but might interact through the weak nuclear force and gravity. WIMPs emerged as the favorite dark matter candidate, largely because they arose naturally from theoretical frameworks that physicists had developed for other reasons. In the 1970s and 80s, theoretical physicists were working on problems in particle physics that had nothing to do with dark matter. One major issue was the so-called hierarchy problem, which asks why gravity is so much weaker than the other fundamental forces. Why can a small magnet overcome the gravitational pull of the entire Earth when lifting a paperclip? The numbers don't seem to make sense unless something is providing a balance, keeping particle masses at reasonable values. One solution to this problem is supersymmetry, often abbreviated as SUSY. This beautiful theoretical framework proposes that every particle we know has a partner particle with different properties. The electron has a partner called the selectron. Quarks have squark partners. Photons have photino partners. These supersymmetric partners would have been created in the early universe but would be much more massive than their ordinary counterparts, which is why we haven't seen them yet at lower energy experiments. If supersymmetry is correct, it could solve several problems in particle physics at once, making the mathematics work out elegantly and providing answers to questions that had troubled physicists for years. Here's where dark matter enters the picture. In most supersymmetric theories, the lightest supersymmetric partner particle, often called the LSP, would be stable. It couldn't decay into anything lighter because, by definition, there's nothing lighter in the supersymmetric family for it to decay into. And this LSP, according to the theories, would interact only through the weak force and gravity, just like a WIMP. In fact, when physicists calculated how many of these particles would have been produced in the Big Bang and survived to the present day, they found something remarkable. The predicted abundance of these supersymmetric particles matched almost exactly the amount of dark matter the universe appears to contain. This coincidence became known as the WIMP miracle, and it made physicists very confident that they had found the answer. The beauty of the WIMP hypothesis was that it connected dark matter to testable theories of particle physics. If supersymmetry was real, and if the LSP was the dark matter, then experiments should be able to find evidence. Three approaches seemed promising. First, direct detection. Build sensitive detectors and wait for the rare occasions when a WIMP passing through Earth happens to bump into an atomic nucleus in the detector, producing a tiny signal that might be measurable. Second, indirect detection. Look for signals from space where WIMPs might be annihilating each other, producing ordinary particles like gamma rays or cosmic rays that we could detect. Third, collider production. Use powerful particle accelerators to create WIMPs by smashing ordinary particles together at such high energies that supersymmetric particles are produced. The Large Hadron Collider, the mighty circular particle accelerator straddling the French-Swiss border near Geneva, was built in part with the expectation that it would discover supersymmetric particles. When it began operating in 2008, and especially after it discovered the Higgs boson in 2012, physicists were excited but also expectant. Supersymmetry should be just around the corner, they thought. The LHC was the right energy scale. Detection should be imminent. Some physicists even joked that it was a machine built to win a Nobel Prize for discovering supersymmetry. But year after year, as the LHC collected data from trillions of particle collisions, no evidence of supersymmetry appeared. No squarks, no selectrons, no photinos. The experiments kept setting limits. ruling out more and more of the parameter space where supersymmetric particles might hide. By now, more than a decade into operations, the LHC has explored much of the range where supersymmetric particles were expected to be found, and they're simply not there. Supersymmetry hasn't been ruled out completely. There are more exotic versions of the theory that might still work, but the simplest, most elegant versions that would have solved the hierarchy problem and provided the WIMP have failed to materialize. Direct detection experiments faced similar disappointments. Teams around the world built ever more sensitive detectors, often placed deep underground to shield them from cosmic ray backgrounds. Experiments like ALUAX in South Dakota, Xenon in Italy, and Pandax in China used tanks of ultra-pure liquid xenon, chilled to extremely low temperatures and monitored by exquisitely sensitive instruments, all waiting to catch the rare flash of light or tiny energy deposit that might signal a WIMP collision. The principle was straightforward. If WIMPs are streaming through Earth constantly, occasionally one should bump into a xenon nucleus hard enough to create a detectable signal. The experiments grew larger and more sensitive over the years. Lux contained about a third of a ton of liquid xenon. Its successor, LAX Zeppelin, or LZ, uses 7 tons of xenon and can detect interactions down to incredibly low energy levels. The sensitivity reached the point where the experiments should have detected WIMPs if they existed in the expected abundance with the predicted interaction strength. But year after year, the results came back null. No WIMP detections. Just tighter and tighter limits on where WIMPs could hide. The experimental window for WIMPy discovery was closing, and closing fast. Indirect detection efforts, looking for evidence of WIMPy annihilation in space, have similarly come up empty. Satellites like the Fermi Gamma Ray Space Telescope have scanned the sky for excess gamma rays from regions where dark matter should be dense, like the galactic center or nearby dwarf galaxies. If WIMPs occasionally collide and annihilate, as some theories predict, they should produce gamma rays at characteristic energies. But no convincing signal has been found despite years of careful observation and analysis. All of this doesn't prove WIMPs don't exist. It's possible they're just heavier or interact more weakly than the theories predicted, hiding in parameter space that hasn't been fully explored yet. But the confidence that once surrounded the WIMP hypothesis has faded. The beautiful connection to supersymmetry, which made WIMPs so compelling, has weakened as supersymmetry itself remains undetected. Every day without a detection makes physicists a bit less certain that WIMPs are the answer. The WIMPy miracle is starting to look like it might have been a mirage, a theoretical coincidence that led the field down a path that, while not necessarily wrong, might not lead to discovery either. The rising star, Axions. As enthusiasm for WIMPs has waned, another candidate has been rising in prominence. The Axion has a very different origin story from the WIMP. It wasn't proposed to explain dark matter at all, at least not initially. Instead, it emerged from efforts to solve a completely different problem in physics, one that had puzzled theorists for years. The fact that it might also be dark matter came almost as a bonus, an unexpected connection that has made the action one of the most intriguing particles in modern physics. The story begins with a problem in the theory of the strong nuclear force, the fundamental force that holds atomic nuclei together. This force is described by a theory called quantum chromodynamics, or QCD. In the 1970s, physicists noticed something odd about QCD. The theory seemed to allow for violations of a symmetry known as CP symmetry, which relates to how particles behave under certain transformations. The weak nuclear force violates CP symmetry. This was known and understood. But the strong force, according to theory, should also violate CP symmetry, and quite strongly at that. Yet experiments showed no evidence of such violations. The strong force seemed to respect CP symmetry perfectly, even though the theory said it shouldn't. This mismatch between theory and observation became known as the strong CP problem. Why would the strong force obey a symmetry that the theory didn't require it to obey? It seemed like an incredible fine-tuning, as if some cosmic dial had been set to exactly 0 when it could have taken any value. Physicists don't like fine-tuning. It suggests something deeper is going on, some principle or mechanism we don't understand yet. In 1977, physicists Roberto Pecce and Helen Quinn proposed an elegant solution. They suggested a new symmetry, now called Pecce-Quinn symmetry, that would naturally force the strong CP violation to be 0. This new symmetry would be spontaneously broken at very high energy scales, and a consequence of this breaking would be the creation of a new field permeating all of space. And if there's a field, quantum field theory tells us there must be an associated particle, the quantum of that field. This particle was the axion, named after a brand of laundry detergent because, as physicist Frank Wilczek later joked, it cleaned up the strong CP problem. Axions would have very unusual properties. They would be extraordinarily light, much lighter than any other particle in the Standard Model except possibly neutrinos. Estimates put the axion mass anywhere from about 1/1,000,000th of an electron volt up to perhaps a milli-electron volt, which is incredibly tiny, 1,000,000,000,000 times lighter than an electron, which is itself nearly 2,000 times lighter than a proton. Because they're so light, axions would barely interact with anything. They would pass through ordinary matter almost completely unimpeded. In fact, they earned the nickname invisible axions because the likelihood of ever detecting them seemed vanishingly small. But here's the beautiful connection. Theoretical calculations suggested that axions should have been produced copiously in the early universe. And if they were light enough and stable enough, the right number of them would survive to the present day to account for dark matter. Unlike WIMPs, which would have been created hot, moving at relativistic speeds, and then cooled down as the universe expanded, axions would be born cold, barely moving at all. This cold axion dark matter would behave exactly as observations require, clumping into halos around galaxies and providing the gravitational scaffolding for cosmic structure. For years, axions were seen as an interesting idea, but not as compelling as WIMPs. The theoretical motivation from the strong CP problem was strong, but the connection to dark matter seemed almost too convenient. And the experimental challenges were enormous. How do you detect a particle that interacts so weakly that it can pass through light years of solid lead without even noticing? WIMPs, at least, might interact through the weak force, giving experimenters something to work with. Axions seemed impossible to catch. But as WIMP searches continued to come up empty, physicists began reconsidering the action, and clever experimenters developed techniques that might actually work. The key insight came from a physicist named Pierre Sicqueville, who realized that in the presence of a strong magnetic field, an action could convert into a photon. The process is exceedingly rare, but if you have enough actions passing through a strong enough magnetic field in the right configuration, you might see a signal. This led to the development of action haloscopes, experiments designed to detect this action-to-photon conversion. The most advanced is the Action Dark Matter Experiment, or ADMX, located at the University of Washington. ADMX uses a powerful magnet and a tunable microwave cavity, all cooled to near absolute zero to reduce thermal noise. If dark matter is made of actions, trillions of them should be passing through the detector every second. Most will pass through without interacting, but occasionally, in the presence of the magnetic field, an action might convert into a microwave photon. When the cavity is tuned to exactly the right frequency, corresponding to the axion's mass, that photon gets amplified, producing a tiny signal that ultra-sensitive detectors can measure. The challenge is that the axion mass is unknown, so the experiment has to scan through a huge range of possible frequencies, searching bit by bit for the needle in the cosmic haystack. It's painstaking work, taking years to cover even a modest range of parameter space. But ADMX has now achieved the sensitivity needed to detect axions in the most theoretically favored mass range. If axions are there with the properties theory predicts, ADMX should find them. Other experiments are taking different approaches. Axion helioscopes like CAST and its successor IAXO look for axions that might be produced in the Sun and then convert to X-rays in a magnet on Earth. The logic is that the Sun's dense, hot core might produce actions through various processes, and these solar actions could be caught and identified. Still, other proposals suggest using quantum sensors to detect the tiny effects axions might have on atomic energy levels, or looking for very subtle signatures in astronomical observations. The action has another advantage over the WIMP. It has to exist, at least if the Peccei-Quinn solution to the strong CP problem is correct. Even if actions aren't dark matter, they should be there waiting to be found. This gives physicists motivation to keep searching regardless of the dark matter connection. As one researcher put it, the action has to be there, or we have other problems. This dual motivation, solving the strong CP problem and explaining dark matter, has made the action increasingly attractive as WIMP searches continue to disappoint. Today, many physicists think actions are the most promising dark matter candidate we have. The theory is well motivated, coming from independent physics considerations. The properties match what we need for dark matter. And, most importantly, experiments are approaching the sensitivity needed to detect actions in the parameter space where theory suggests they should be. The next decade might tell us whether the universe's invisible majority is made of these ghostly, nearly massless particles that were born in the Big Bang and have been streaming through space ever since, invisible messengers carrying secrets from the dawn of time. The Hunt Detection Experiments. The search for dark matter has become one of the grand experimental efforts of modern physics. Around the world, teams of scientists are building detectors, analyzing data, and pushing the boundaries of measurement precision, all in pursuit of particles that stubbornly refuse to reveal themselves. These experiments represent an interesting challenge in science. How do you study something that barely interacts with anything? How do you catch a ghost? Direct detection experiments take the straightforward approach. Build a sensitive detector and wait. The idea is elegantly simple. If dark matter particles are constantly streaming through Earth, occasionally one should collide with an atomic nucleus in your detector. That collision would impart a tiny amount of energy to the nucleus, causing it to recoil. If you can detect that recoil, you've caught your dark matter particle in the act. The challenge lies in the word occasionally. Dark matter interacts so weakly that even with trillions of particles passing through your detector every second, you might see only a handful of interactions per year. And you need to distinguish those rare signals from all the other things that can mimic them. This is why direct detection experiments are built deep underground. Cosmic rays, high-energy particles raining down from space, can create signals that look like dark matter interactions. By placing detectors a mile or more underground, as with LOEX Zeppelin in South Dakota or Xenon in Italy's Gran Sasso Laboratory, the overlying rock shields the detector from most cosmic rays. You also need to use the purest possible materials to minimize radioactive contamination that could produce background signals. The xenon in these detectors is processed to remove even trace amounts of radioactive isotopes. The tanks themselves are made from carefully selected materials with minimal radioactivity. When a particle does interact in a xenon detector, it produces both light and ionization. A WIMP collision with a xenon nucleus creates a specific signature: a small amount of light from the recoiling nucleus, followed by a second pulse of light when the ionization electrons drift to the top of the detector and are extracted. The ratio of these two signals helps distinguish genuine WIMP interactions from backgrounds like gamma rays or random radioactive decays. Experimenters have spent decades refining these techniques, learning to identify and eliminate backgrounds, pushing sensitivity to levels that seemed impossible just years ago. And yet, despite all this effort, direct detection experiments have seen nothing convincing. LOEX collected data for years and saw no dark matter. Xenon 1T, one of the most sensitive experiments ever built, reported some tantalizing hints of excess events, but nothing definitive. The newest generation, LUX Zeppelin, with its 7 tons of xenon, began taking data recently and will search with unprecedented sensitivity. If WIMPs exist in the parameter space that remains unexplored, LZ should find them. But each null result narrows the possibilities. Pushing allowed WIMP properties into corners where they become increasingly contrived. Other direct detection experiments use different target materials. Super CDMS uses ultra-cold crystals of germanium and silicon, chilled to just a few hundredths of a degree above absolute zero. At these temperatures, even tiny energy deposits from particle interactions create measurable heat pulses and phonons that propagate through the crystal. This approach is particularly sensitive to low-mass dark matter particles, which might not create enough signal in xenon detectors, but could still be caught by the exquisite sensitivity of cryogenic crystals. The upcoming Super CDMS SNOLAB detector, currently under construction in a nickel mine in Ontario, Canada, will push this technique to its limits. Indirect detection takes a different approach. Rather than waiting for dark matter to hit a detector, these experiments look for the products of dark matter interactions happening elsewhere in the universe. Some theories predict that when two dark matter particles collide, they can annihilate, converting their mass into energy and creating ordinary particles like photons, neutrinos, or electron-positron pairs. These annihilation products could be detected from Earth, providing indirect evidence of dark matter. The challenge with indirect detection is distinguishing dark matter signals from ordinary astrophysical sources. The galaxy is full of processes that create gamma rays, cosmic rays, and neutrinos. How do you pick out the faint signature of dark matter annihilation from this cacophony of signals? Experimenters focus on places where dark matter should be particularly dense, like the galactic center or nearby dwarf galaxies that are thought to be dominated by dark matter. They look for excess signals at specific energies or from specific directions that would be hard to explain with ordinary astrophysics, but would be natural if dark matter were annihilating. The Fermi Gamma Ray Space Telescope has spent more than a decade scanning the sky in gamma rays, looking for these signatures. There have been some intriguing hints. An excess of gamma rays from the galactic center, for instance, that could potentially be explained by dark matter. But alternative explanations involving pulsars or other conventional sources remain viable. The IceCube Neutrino Observatory, a cubic kilometer of instrumented ice deep under the South Pole, looks for neutrinos from dark matter annihilation. No convincing signal has emerged yet, but the searches continue, setting ever tighter limits on how often dark matter particles could be annihilating. For action detection, the experimental landscape looks quite different. ADMX and similar experiments essentially turn dark matter detection into a radio astronomy problem. Axions converting to photons in a magnetic field would produce extremely faint radio signals at very specific frequencies. The experiment becomes a search for these whisper-quiet signals hidden in the noise. To improve sensitivity, ADMX uses superconducting quantum interference devices, or SQUIDs, as amplifiers. Devices that operate at the quantum limit of measurement precision. The entire apparatus is cooled to millikelvin temperatures using helium-3 refrigerators, creating an environment where the thermal noise drops low enough that axion signals might peek through. The scanning process is slow. To cover the range of possible axion masses, ADMX adjusts its cavity resonance frequency by moving tuning rods, searching step by step through the parameter space. Each frequency range might take weeks or months to explore thoroughly. But progress continues. ADMX has already ruled out certain action mass ranges and is systematically working through the regions where theory suggests actions are most likely to be found. If actions make up even a significant fraction of dark matter, the experiment should see them within the next several years. Other action experiments use different strategies. Abracadabra uses a different type of resonant detection, while Casper looks for the effects of action dark matter on nuclear spins. Each approach has its own sensitivity window, covering different possible action masses. Taken together, these experiments are mapping out the axions in parameter space with increasing thoroughness, hunting for the telltale conversion of these ghostly particles into photons we can measure. Perhaps the most ambitious approach is trying to create dark matter at particle accelerators. The Large Hadron Collider can smash protons together at such enormous energies that, if dark matter particles are light enough, they might be created in the collisions. The trick is that dark matter particles, once created, would simply stream out of the detector without being seen directly. But physicists can infer their presence through missing energy and momentum. When particles collide and create something invisible, the visible particles that are also produced carry less total energy and momentum than they should. By carefully accounting for all the visible particles and finding that the sums don't balance, experimenters can infer that invisible particles were also created. LHC experiments have looked for such signatures in countless collision events, searching for evidence of WIMPs or other exotic particles. The fact that nothing has been seen places constraints on how heavy dark matter particles can be if they're produced through the interactions available at the LHC. These constraints complement the direct and indirect detection efforts surrounding the dark matter problem from multiple angles, narrowing the possibilities even as the particles themselves remain stubbornly hidden. The hunt for dark matter is a test of experimental ingenuity and patience. It requires building detectors more sensitive than anyone thought possible, analyzing data with exquisite care to distinguish signal from background, and maintaining faith that the quarry exists even after years of null results. It's science at its most challenging and its most fundamental. The search for something we're convinced must be there, even though we've never seen it directly, guided by the evidence of its gravitational influence and the conviction that the universe must make sense. Alternative theories. Not everyone is convinced that dark matter exists. A small but vocal minority of physicists and astronomers have proposed that instead of invoking invisible matter to explain observations, perhaps we should modify our understanding of gravity itself. After all, they argue, we've never detected dark matter directly. We've inferred its existence by assuming that Einstein's theory of gravity is correct and applying it to galaxies and clusters. But what if the theory breaks down on galactic scales? What if gravity works differently when dealing with the enormous distances and weak accelerations characteristic of galaxy rotation? The most prominent alternative theory is modified Newtonian dynamics, or MOND, proposed by physicist Mordechai Milgrom in the early 1980s. MOND starts from a simple observation. Galaxy rotation curves show deviations from Newtonian predictions at a characteristic acceleration scale. Below this scale, about 1/10,000,000th of the acceleration we experience from Earth's gravity, the rotation curves flatten out. Milgrom suggested that perhaps gravity itself changes behavior at such low accelerations, becoming stronger than Newton's or Einstein's theories predict. If you modify the law of gravity in just the right way, you can explain galaxy rotation curves without invoking dark matter. The flat rotation curves, the primary evidence that convinced Vera Rubin and others that dark matter existed, emerge naturally from the modified gravity law, and MAOND is remarkably successful at predicting rotation curves for a wide variety of galaxies. Given just the distribution of visible matter MOND can tell you what the rotation curve should look like, and it's often right. This is impressive, and it's why MOND continues to have adherents despite the mainstream consensus favoring dark matter. But MOND has serious problems when you look beyond galaxy rotation. It struggles to explain galaxy clusters, where the mass discrepancy is much larger than in individual galaxies. Even with modified gravity, you would still need additional invisible mass to hold clusters together. The bullet cluster poses particular problems for MOND. The separation between visible matter and gravitational mass in that system is hard to explain without actual dark matter that can pass through ordinary matter without interacting. MOND also has trouble with the cosmic microwave background. The precise pattern of temperature fluctuations in the CMB depends on the ratio of dark matter to ordinary matter in the early universe. MOND doesn't explain these patterns as naturally as dark matter does. Various attempts have been made to develop relativistic versions of MOND, theories that incorporate modified gravity into a framework compatible with general relativity. TVIS, or tensor vector scalar gravity, is one such attempt. But these theories tend to be complicated, requiring multiple new fields and adjustable parameters. And they still can't explain all the observations that dark matter explains so elegantly. Each new piece of evidence seems to fit naturally into the dark matter paradigm, while requiring ad hoc modifications to alternative theories. Other modified gravity theories have been proposed over the years, each trying to match observations without invoking dark matter. Entropic gravity suggests that gravity might emerge from thermodynamic principles rather than being a fundamental force. Some theories propose extra dimensions or modifications to general relativity on cosmic scales. But none of these alternatives have achieved the explanatory power of dark matter. They might explain one or two observations, but fail to account for the full range of evidence. The scientific consensus is that while alternative theories are worth exploring, good science requires considering multiple possibilities. The evidence overwhelmingly favors dark matter. Too many independent observations from too many different types of measurements all point to the same conclusion. Galaxy rotation curves, cluster velocities, gravitational lensing, the cosmic microwave background, structure formation, even the evolution of the universe over time, all make sense if dark matter exists, and all require awkward explanations if it doesn't. This doesn't mean dark matter advocates are closed-minded or refuse to consider alternatives. It means that the evidence has accumulated to the point where dark matter provides by far the best explanation for what we observe. If someone could develop a theory that explained all the observations as naturally as dark matter does, without requiring invisible matter, it would be taken very seriously. But so far, no alternative has come close to matching dark matter's explanatory power. The situation is somewhat analogous to what happened with Neptune in the 19th century. Observations of Uranus showed that its orbit deviated from what Newton's laws predicted. Astronomers could have proposed that Newton's laws needed modification at large distances from the Sun. Instead, they hypothesized that an unseen planet was perturbing Uranus's orbit. When telescopes were pointed at the predicted location and Neptune was discovered, It vindicated the approach of invoking invisible matter rather than modifying gravity. With dark matter, we're in a similar situation, except the invisible matter is much harder to detect directly. We have overwhelming circumstantial evidence from multiple sources, all pointing to the existence of dark matter. The question isn't whether something is there, it clearly is, but rather what it's made of. Is it particles, and if so, which ones? Or is there some other explanation we haven't thought of yet? Either way, the mystery remains, calling out for resolution. Implications and mysteries. The existence of dark matter has profound implications for how we understand the universe. It means that everything we can see, measure, and interact with directly is just a small fraction of what's out there. We're living in a cosmos dominated by the invisible, where the familiar matter that makes up our bodies, our planet, and all the stars we can see is barely a trace component. This is humbling, certainly, but it's also fascinating. It tells us that reality is far richer and stranger than it appears. Dark matter fundamentally shaped the universe we inhabit. In the early cosmos, just after the Big Bang, matter was distributed almost uniformly. Almost, but not quite. There were tiny density variations, regions where matter was slightly more concentrated than average, and regions where it was slightly less dense. Without dark matter, these variations would have been smoothed out by radiation pressure and other effects. The universe would have remained more or less uniform, with no galaxies, no stars, no planets. But dark matter, immune to radiation pressure and interacting only through gravity, could clump immediately. Where dark matter concentrated, it created gravitational wells. Ordinary matter, following the gravitational pull, fell into these wells. Over hundreds of millions of years, the matter collapsed further, forming the first stars and galaxies. The distribution of dark matter determined where galaxies would form, creating the cosmic web of filaments and voids that persists to this day. Without dark matter, the universe would be a very different place. It's possible that galaxies and stars wouldn't have formed at all, at least not in time for elements like carbon and oxygen to be created and dispersed. Without those elements, life as we know it couldn't exist. In this sense, we owe our existence to dark matter. It provided the gravitational scaffolding that allowed structure to form, that gathered gas into galaxies and stars, that enabled the chemistry necessary for life. We're not just living in a universe with dark matter, we're living in a universe made possible by dark matter, shaped by its invisible presence from the earliest moments to the present day. Yet despite dark matter's importance, its nature remains mysterious. We don't know what dark matter particles are. We don't know their mass, their interaction strength, or even definitively that they're particles at all, though that's the leading hypothesis. We don't know how they were created in the Big Bang, though we have ideas. We don't know if they decay, though they must be at least very long-lived. We don't know if there are multiple types of dark matter or just one. All of these questions remain open, waiting for the experiments currently running or planned to provide answers. There's also the question of whether dark matter can form structures more complex than halos. Could there be dark matter planets or dark matter stars or even dark matter life? Most physicists think not. because dark matter doesn't have the ability to lose energy and collapse into dense configurations like ordinary matter does. But there are speculative ideas about forms of dark matter that might interact with themselves through some dark force, analogous to electromagnetism but acting only on dark matter particles. Such self-interacting dark matter could potentially form complex structures, though there's no evidence for this yet. Another mystery is the relationship between dark matter and dark energy. These two dark components dominate the universe's mass-energy budget, yet they seem to be completely different phenomena. Dark matter clumps and creates gravitational attraction, helping structures form. Dark energy spreads uniformly and creates gravitational repulsion, driving the accelerated expansion of the universe. Why should both exist? Why should they have comparable densities today, even though they evolve differently over cosmic time? Is this a coincidence, or is there some deeper connection we don't understand? The distribution of dark matter within galaxies also presents puzzles. Computer simulations of dark matter halo formation predict that dark matter should be very concentrated near galactic centers, creating what's called a cuspy density profile. But observations of some galaxies, particularly small dwarf galaxies, suggest smoother, more constant density cores rather than cusps. This discrepancy might be telling us something important about dark matter's properties. Or it might just mean we don't fully understand how ordinary matter affects dark matter through gravitational interactions. The question remains debated. There's also the question of what happens to dark matter that falls into black holes. Black holes consume everything, including dark matter. Over billions of years, do black holes gradually accrete significant amounts of dark matter? Could some black holes be substantially more massive than their visible matter accretion would suggest? And what happens to the information contained in dark matter particles when they fall into a black hole, given that black holes seem to scramble information in ways we don't fully understand? These questions highlight how much we still don't know. Dark matter has transformed from a mystery about why galaxies rotate the way they do into a fundamental puzzle about the nature of matter itself, the evolution of cosmic structure, and the ultimate composition of reality. Solving the dark matter mystery won't just tell us what one type of particle is. It will likely reveal new physics, new forces, new principles that operate beyond the standard model of particle physics we've spent the last century developing. Closing reflections, and so we drift toward the end of our journey through the invisible universe. We've traveled from Frey's Zwicky's puzzling observations in 1933 through Vera Rubin's patient mapping of galaxy rotation to the underground laboratories where physicists today search for particles that refuse to be caught. We've explored the evidence from multiple sources, considered the candidates that might make up dark matter, and pondered the implications of living in a universe where most of what exists cannot be seen. Dark matter reminds us that for all our scientific progress, for all our technological sophistication, the universe still holds profound mysteries. We've achieved remarkable things. We've split atoms, decoded DNA, landed robots on Mars, detected gravitational waves from colliding black holes, and photographed the first moments after the Big Bang. Yet we still don't know what most of the universe is made of. This should humble us, certainly, but it should also fill us with wonder and excitement. There are still frontiers to explore, still questions to answer, still discoveries waiting in the darkness. Think about what dark matter's existence means. Right now, as you rest, dark matter particles are passing through your body. Particles that were created in the Big Bang, that have been traveling through space for more than 13 billion years, are flowing through you like a river. They carry no message, interact with nothing, care not at all for our existence. And yet their collective gravity shaped the galaxy in which we live, determined where stars would form, made possible the chemical elements that compose our bodies. We are downstream from dark matter in the deepest possible way, products of a universe structured by forces and substances we're only beginning to understand. The search for dark matter continues. Even as you sleep tonight, detectors deep underground are watching, waiting, recording. Satellites in orbit scan the sky for signals. Physicists analyze data, develop new theories, design next-generation experiments. The experiments running now have already ruled out huge swaths of parameter space, narrowing the possibilities for what dark matter might be. The next generation will probe even deeper, reaching sensitivities that push against fundamental limits of measurement. If WIMPs, or Axions, exist in the ranges theory predicts, they will be found. And when dark matter is finally detected directly, when we catch these elusive particles in the act and can study their properties in detail, it will be one of the great triumphs of human curiosity and ingenuity. It will open new windows onto reality, perhaps revealing new forces, new symmetries, new principles that govern existence at its most fundamental level. It might point the way to physics beyond the standard model, to unified theories that connect to forces we thought were separate, to understanding of how everything emerged from the Big Bang's first moment. But even if dark matter remains elusive for years or decades more, even if the mystery persists longer than we'd like, that's okay too. Some of the deepest questions take time to answer. The universe doesn't yield its secrets easily, nor should it. The journey of discovery, the process of gradually peeling back layers of mystery through careful observation and clever experimentation, is valuable in itself. It's what makes us human, this desire to understand, to know, to see beyond the apparent into the hidden truth beneath. As you drift towards sleep, or if you're still awake, consider this. You're part of a species that looked at galaxy rotation curves, at the motion of distant clusters of light, and deduced the existence of an entirely new component of reality. Humans, with our limited senses that evolved to hunt and gather on an African savanna, have developed tools and techniques that reveal invisible matter permeating the cosmos. We've extended our perception far beyond what biology gave us, using mathematics and physics as prosthetic senses that let us see the unseeable. That's remarkable. That's something to be proud of, something to marvel at as your consciousness fades and sleep approaches. The universe is vast and ancient and full of wonders. Dark matter is just one of them, one of the great unknowns that calls out for understanding. There are others: dark energy, the nature of quantum mechanics, the origin of life, the possibility of other universes. Each of these mysteries invites exploration, promises discovery, rewards curiosity with insight. The journey is far from over. The story of what humans will learn about the cosmos is still being written. chapter by chapter, observation by observation, experiment by experiment. So rest easy tonight, knowing that you've explored one of the deepest mysteries in modern science. You've followed the evidence from visible galaxies to invisible halos, from galaxy clusters to cosmic web, from the dawn of time to the present day. You've learned about the particles that might compose dark matter and the experiments hunting for them. You understand now that the universe is far stranger and more mysterious than it appears. That the visible is just a small part of what exists. That darkness holds as much reality as light. The iron in your blood, the calcium in your bones, the oxygen in every breath. All of these were created in stars and dispersed into space by supernova. Those stars formed in galaxies held together by dark matter. Those galaxies formed around dark matter halos that condensed in the early universe. You are stardust, yes, but you're also the product of dark matter's gravitational influence, shaped by forces you cannot see across billions of years. You are, in the deepest sense, a child of the cosmos, both visible and invisible, both understood and mysterious. If you're still listening, if sleep hasn't quite claimed you yet, thank you for joining me on this journey into the invisible universe. If these explorations bring you peace, if they help you unwind at the end of your day, or if they simply satisfy your curiosity about the cosmos, please consider liking this video and subscribing to the Sleepy Science Society. It helps others find their way here too, others who might be looking for a gentle way to learn, a calm voice speaking of cosmic wonders as they drift toward dreams. Sleep well, rest deeply, and remember, the universe is far larger, far stranger, and far more wonderful than anything we can see. The darkness holds mysteries still waiting to be discovered, and somewhere in that darkness, dark matter flows silently on, shaping galaxies, enabling stars, making possible the emergence of complexity and consciousness and curious creatures like us who look up at the night sky and wonder what lies beyond. Good night.